In this video, we're diving into simple linear regression with the head-brain dataset. We'll learn how to predict brain weight based on head size using the least square method. If you're curious about machine learning, data science, or statistics, this is the perfect video for you. Let's get started. First, let's start by importing the libraries we'll be using. Here, we have three important ones: NumPy, Pandas, and Matplotlib. Let me break them down quickly. NumPy, short for Numerical Python, is a powerful library for handling numerical data. It's great for performing operations on arrays and matrices, tools you'll often use in machine learning. Next is Pandas. Think of it as Excel for Python, but much more powerful. It helps us organize and manipulate data effortlessly using data frames, which are essentially tables. Finally, there's Matplotlib. This library is your go-to for creating visualizations. Whether it's simple plots or advanced graphs, Matplotlib has got you covered. We're using the head-brain dataset, which contains 237 observations with 4 columns: gender, age range, head size in cubic centimeters, and brain weight in grams. Our primary goal is to find the relationship between head size and brain weight. This involves calculating a regression line, predicting brain weights, and evaluating the model. All right, let's dive a little deeper into the math behind linear regression. The formulas for finding the slope B1 and intercept B0 are derived using calculus-based minimization techniques. But what does that actually mean? Simply put, these formulas aim to minimize the squared differences between the actual and predicted values. First, the numerator of B1. This term represents the covariance between our independent variable x, head size, and our dependent variable y, brain weight. Covariance measures how changes in one variable are associated with changes in another. If it's positive, that means as x increases, y also tends to increase. That's what we call a positive correlation. Conversely, a negative covariance indicates that as x increases, y decreases. Next is the denominator of B1. This term accounts for the spread of the independent variable x, basically its variance. Why is this important? Well, if x has a small variance, even tiny changes in x will cause big shifts in y, resulting in a steeper slope. On the other hand, if the variance is large, the slope will be gentler. And finally, we have the intercept B0. This is the value of y when x is 0. It provides a baseline or starting point for our regression line. This formula tells us how the regression line fits the data. Once we have B0 and B1, we can make predictions for y given any value of x. Understanding these components is key to interpreting linear regression. Now, let's put this knowledge into practice by calculating these values for our dataset. Now let's calculate the slope B1 and intercept B0. We compute the mean of x and y and apply the formulas. Next, we'll visualize the data and the regression line. The scatter plot shows the actual data points, while the regression line represents the predicted relationship based on the calculated coefficients. X values are generated over a range for a smooth line, and the plot is labeled for clarity. This helps assess how well the line fits the data. To assess our model, we calculate the R-squared score, which measures how well the regression line predicts brain weight. Total variance measures the overall spread of actual brain weight values around their mean, representing the total variability in the data. Residual variance measures the differences between the actual brain weights and the values predicted by the regression model, indicating the unexplained variability. A smaller residual variance compared to total variance signifies a better model fit. A score closer to 1 indicates a smaller residual variance relative to the total variance, meaning the model's predictions closely align with the actual data. This low ratio signifies that most of the variability in the brain weight is accounted for by the regression line, reflecting a strong correlation and a good fit to the data. The R-squared score is approximately 0.639, meaning 63.9% of the variation in brain weight is explained by head size. A decent fit. That's it for this video. We covered the head-brain dataset, derived a regression line using the least squares method, and evaluated its accuracy with R-squared method. Thanks for watching, and see you in the next one.